Hi, this is Professor Len Kelly, and in this presentation I want to explore the underpinnings of how to use indicator variables when wanting to include a qualitative predictor variable in a multiple linear regression model. Of course, we've already introduced the multiple linear regression model with p parameters, that is p minus 1 predictor variables. We know what our goal is in trying to estimate such a model. We want to minimize the sums of squares error. We know what p represents in this particular notation. P is the number of parameters in our model. The random error term epsilon sub I we've discussed at great length. We've also introduced matrix notation to allow us to capture the multiple linear regression model, and we've discussed how to go about finding the estimated regression coefficients that provide the ordinary least squares fit. And in this particular case, you notice that the column vector of estimated regression coefficients B can be found by taking x transpose x inverse times x transpose y. And of course, the proviso is that x transpose x inverse exists. We've also discussed in great detail the fact that these estimators, this column vector B, is an unbiased estimator of the parameters in the model that we're trying to estimate. That is, their expected value is equal to the value of the parameters that we're trying to estimate. We have discussed how to find the variance covariance matrix associated with those estimators, and how to find an estimated variance covariance matrix by substituting mean squared error for the unknown sigma squared. Again, we notice that in this variance covariance matrix, the matrix x transpose x inverse plays a role. And so clearly we know that x transpose x inverse is important in building and analyzing linear regression models. But we want to go back to our linear algebra review and remember that not every square matrix has an inverse. In fact, the square matrix R by R has an inverse only if its rank is equal to R. That is, only if the number of, or the columns in the matrix are linearly independent. So we know that there are situations in which x transpose x inverse may not exist. And naturally, if we want to build and analyze multiple linear regression models, we need to be on our guard to ensure that the matrix x transpose x in fact does have an inverse. And we can guarantee that by making sure that the column vectors associated with that matrix x transpose x are linearly independent. Now, we've already introduced the notion of indicator variables, and I've told you previously that I wanted to spend a little more time talking about them in detail, and that time has come. But let's remember that we can certainly utilize qualitative variables in a multiple linear regression model, and there are many. We've seen some in the examples that we've worked, and we're going to see that same example again in this lesson. But indicator variables are necessary to be used when we want to use qualitative variables in a regression model. We sometimes call these dummy variables. And it's the introduction and use of these indicator variables that will allow us to integrate the meaning and to interpret the meaning of the indicator variables, and hence the qualitative variables that we might want to include in a model. Now, if we have a qualitative variable with A levels and we use A indicator variables, then it's going to turn out that the columns of x transpose x are dependent. And we'll see an example of that in just a moment. Consequently, If that's the case, if the column vectors of our X transpose X matrix are dependent, then we won't be able to find the estimated regression coefficients because we won't be able to find the inverse of X transpose X. We cannot find the variance covariance matrix or the estimated variance covariance matrix associated with the estimators in the column vector B. And we couldn't conduct much of the inferential analysis that we've discussed heretofore associated with multiple linear regression models. So ensuring that X transpose X actually has an inverse is vitally important. And when we talk about the use of qualitative variables as predictor variables in a multiple linear regression model through the introduction of indicator variables, we have to be very careful not to use all the indicator variables associated with all the quote A levels of the qualitative variable of interest. To illustrate, let's look at an example that we've already seen and try to get into the nitty-gritty of the use and interpretation of indicator variables in this example. Again, we've seen this before. We're interested in building a model that will allow us to predict and get a sense for the relationship between the housing payment made by families in a particular geographic region as a function of the explanatory variables total debt, family size, and location. Now this is the reduced model that we've examined earlier. You'll notice that some of the original variables in our data set have been eliminated. And here is the original data. You recognize that ownership, first income, second income, and utilities, we want to eliminate those variables. So I have the original data sheet here and then a reduced data sheet. And we've already discussed the idea of the introduction of these four indicator variables, loc1, loc2, loc3, and loc4. And we can give them values, that is location 1 would be equal to 1 if the family lives in location 1, otherwise a 0. Location 2 will be a 1 if the family lives in location 2, otherwise a 0, etc. And we can build those location indicator variables, loc1, 2, 3, and 4, using a series of if statements. You can work your way through that. The bottom line is I've done it for you already. And keep in mind what the locations are. You see the comment in the little red triangle here for location. So we know 1 is southwest, 2 is northwest, 3 is northeast, and 4 is southeast. And those are just indicators. Bottom line is I've eliminated some of the variables now that I've introduced these location variables. Notice in particular that the original location variable is no longer needed. In fact, the original location variable is just a coding. And so as we discussed, there's no meaningful interpretation associated with those particular choice of codes 1, 2, 3, and 4. But now that we've introduced these indicator or dummy variables, they certainly have some interpretive meaning, some quantitative meaning, as we'll see as we make our way through the construction of the model and delve a little more deeply into the use and interpretation of these indicator variables. But the bottom line is now I can go ahead and I can build a regression model using this data set that appears on this worksheet called MLR Data Reduced. But before I do that, I want to illustrate for you the difficulty that you would encounter if in fact you attempted to use all four of these indicator variables. Now remember, location had 4 levels. 1, 2, 3, and 4, we coded them. Southwest, northwest, northeast, southeast. So it has 4 levels. And the temptation might be to use all 4 indicator variables in our model. So what I've done on this worksheet called MLR data reduced with a constant is I've introduced that column of ones, which you know is necessary in order to pick up the intercept term in our multiple linear regression model. And now over here I just took and put the data set in this location starting in column L through R. And then off to the right here I actually did the arithmetic. Well, I had Excel do it using the matrix multiplication array function in Excel. I multiplied x transpose x, and of course here's the result in this now 2, 4, 6, 7 by 7 square matrix. And the question is, does this 7 by 7 square matrix have an inverse? And the answer is, even though Excel will compute an inverse for it, it in fact does not. And that's what I've highlighted here in the yellow text box. So it's unfortunate, but if we were to actually ask Excel to compute the inverse of this matrix x transpose x that I've formed here in this location, it'll do it. It'll be very unstable, but it'll do it. The bottom line is it should not, but it does. So we do need to be on guard. And what I want you to notice is, if I take a look at the sum of these 4 columns, so I've got these 4 column vectors in my matrix x transpose x, and if I sum them, here's the result. So notice that column 1 in x transpose x can be expressed as the sum of these columns, I guess it'd be 2, 3, columns 4, 5, 6, and 7. So if we actually did the summation, look up here in the formula bar, I take the sum of these 4 columns and add them, and here's what I get. And notice that that's precisely equal to the first column. So clearly there's a linear dependence amongst the column vectors in the matrix x transpose x. And because of that, that matrix that you see here, this 7 by 7 matrix, formed by taking x transpose x using all 4 indicator variables, does not have an inverse. Like I said, Excel will compute it. If you use the M inverse function, Excel will actually compute the inverse, but it's very unstable. You could do that for yourself. The bottom line is, you know, because you've had a course in linear algebra, that if the column vectors of a matrix, a square matrix, are linearly dependent, then that matrix does not have an inverse. So even though Excel wants to compute an inverse for it, we realize that x transpose x inverse does not exist if we use all 4 dummy variables. And so in this particular case, we want to make sure that we use a minus 1 or 3 of the dummy variables. And the rationale is so that x transpose x inverse exists. We can then find the estimated regression coefficients. We can do the inference that we want to do. We can build the variance covariance matrix associated with those estimators, etc., etc. Now, just a quick word about the coding, and this, I hope, brings the point home. We've coded in this data set the location, original location variables of 1, 2, 3, or 4 corresponding to southwest, northwest, northeast, southeast. We could have used any codes, A, B, C, and D. The bottom line is those codes are meaningless as quantitative variables. So we certainly don't want to use the original location variable in our model because we could have used different codings for that variable. It is clearly a qualitative variable. So whenever you have a qualitative variable, remember you have to use indicator variables to take care of its inclusion in a multiple linear regression model, but you only want to use one less than the number of levels, one less number of indicator variables for the number of levels of the qualitative variable that you're interested in including in your model. Well, that's a mouthful, but I think you get the idea, and the example is certainly highlighted. So it's clear we can't use all four. I hope it's clear that we can't use all four indicator variables. If we do, we run into serious computational problems, namely that x transpose x will not have an inverse. So again, I'm repeating myself here, but if you want to introduce a qualitative variable that has a levels, then you must use only a minus 1 indicator variables. That should be a plural variables. The choice of which indicator variables to use, of course, is a personal one, but the interpretation of the results is definitely influenced by that result, as you'll see. For example, if we take and build a model, and we've done this previously, so it's going to be a repeat in some sense for you, but if we build a multiple linear regression model using the 3 indicator variables, loc1, loc2, and loc3, and we've seen this before, here's what we get. So here's the data set over here to the left, and what I did was I used the data analysis tool pack in Excel. So if I go to data and go to the data analysis, and we've been through this before, and scroll down and get the regression procedure and enter our y variable, which is our monthly payments, grab them all down to 503, and then our inputs for our x variables. In this case, I went family size debt, and notice I'm going to use loc1, loc2, and loc3, and again that's going to go down to column 503. So let me just type it rather than scrolling. 503, and I did grab the labels, and if I send this to let's call it reduced MLR out for output, and we hit OK, it's going to cook, and it's going to produce output that looks something like this. Now I've doctored mine up a bit, but the bottom line is you're going to get some output that looks like this, and here are the estimated regression coefficients associated with that model using indicator variables loc1, loc2, and loc3. And now the question becomes, what do these estimated regression coefficients associated with location 1, location 2, and location 3 mean? That is, how do we interpret their meaning? Well, let's consider a family of size 4 with $4,000 in debt living in the 4 different locations associated with this multiple linear regression model. And so we'll go back to our workbook called Qualitative Payment LMR. This Excel workbook, of course, will be available for you in the lesson section of our classroom. And let's take a look at the column vector associated with a family of size 4 with $4,000 of debt living in location 1, and see what its estimated housing payment will be. And an easy way to do that, folks, is to use a function called the sum product function. The sum product basically does what it says. It takes products and sums them up, and it does it element by element. So what I've done in this cell here, J13, you can see is I've used the sum product of B17 through B22, which are the estimated regression coefficients, comma, J5 through J10, which are the values of the predictor variables in this particular example, where we want to look at the response associated with a family of size 4 with $4,000 of debt living in location 1. Now notice the loc 1 is a 1, loc 2 and loc 3 are zeros. And when I compute that sum product, give it a try. Notice also that I used absolute reference for these cell references, because what I'm going to do then is I simply took and drug that formula over to get these other results. The bottom line is a family of size 4 with $4,000 of debt living in the southwest sector would have an estimated housing payment of $957.58. That same family living in location 2 would have an estimated housing payment of $1,066.92. If that same family lives in Sector 3, that is the northeast region of our neighborhood, then its estimated housing payment, monthly housing payment, would be $876.93. And for that family that lives in Sector 4, its estimated monthly housing payment would be $706.66. So what do these regression coefficients 250, 360, and 170 represent? Well, they represent the difference between the family's payment that lives in Sector 1 versus Sector 4. Now notice, when I do this arithmetic of taking the average payment of the family that lives in Sector 1 minus the family that lives in Sector 4, I get $250.92, which is precisely the estimated regression coefficient associated with the loc 1 indicator variable. Similarly, if I take the difference between the average payment made by families of size 4 living in Sector 2 versus that same family living in Sector 4, I get the 360.26 value, which is the estimated regression coefficient associated with the indicator variable loc 2. And lastly, the 170 represents the difference associated with living in Sector 3 versus living in Sector 4. So these estimated regression coefficients can be interpreted in light of the benchmark. The benchmark being Sector 4, which is the indicator variable which was left out of our model. So the indicator variable that we leave out of our model actually becomes the benchmark against which the estimated regression coefficients associated with the other indicator variables can be interpreted. So, assuming that all other variables are held constant, that is, we looked at the same family profile, family of size 4, $4,000 of debt, and then we varied the location, and it turns out then that the estimated regression coefficients of the indicator variables actually then represents the delta between the location for which the indicator variable has that coefficient and the location which we did not include in the model. And you can go through and verify that arithmetic so that you can walk away with the notion, with the belief, that the estimated regression coefficients of the indicator variables that are used in the model actually represent the difference between the response associated with those, in this particular case, those locations that are included in the model versus that location which was not included in the model. And that, my friends, is, the way that we can actually garner the influence that location, that original qualitative variable location has on the response variable that we're interested in this particular regression model. So, to ensure that you understand how to use the regression output associated with these indicator variables, I would invite you to run the model using using loc 2, loc 3, and loc 4 as the 3 indicator variables in the model, and leaving out location 1. And I would like you to, wrestle with, what do you notice when you do that? Well, of course, I've done that already. Again, I think it would be useful for you to do that, but here's what the result looks like. Let me, again, I had to rearrange the data a little bit. So I have a worksheet here called Multiple Linear Regression Data Reduced Loc 1. And what you see here is now I have as my predictor variables family size, debt, location 2, location 3, and location 4. And notice location 1 is not used in this particular model. And so again, we go back to the data analysis toolpack, we run our regression, we identify our response variable, we identify our predictor variables, and by now you're experts at doing this, so I won't bore you with it again, and you get the loc 1 output, what I call the loc 1 MLR output. And what that's referring to is a model in which the location 1 dummy variable is not used. And so the interpretation of our estimated regression coefficients associated with our indicator variables loc 2, loc 3, and loc 4 give us a sense of the behavior between those locations 2, 3, and 4 versus location 1. So again, I've done the arithmetic for you over here, and I would invite you to go through that arithmetic. But here are the y-hats associated with a family of size 4 with $4,000 of debt living in location 1. Now, if the family lives in location 1, then loc 2, loc 3, and loc 4 are all zeros. So if I take the sum product of this vector with the coefficient vector, which is what I've done in this cell, notice the formula bar, I still get my same 957.58 as I did previously. I still get, for families that live in location 2 of size 4 with $4,000 of debt, I still get my 1,066.92, etc. for that same family, that same family profile that lives in location 3 or location 4. But now you got to remember that I'm looking at the difference versus oh shoot, I have a typo there, don't I? The difference, oh yeah, this is versus location 4, what I've done before, and here's the difference versus location 1, which is, what I want to look at in light of this model, because it's the location 1 dummy variable that has been eliminated from this particular version of the model. And notice what I get. The difference between the payment for this family of size 4 with $4,000 of debt living in location 2 versus location 1 is $109.33. So again, take a look at the formula bar here. So I've taken K12, which is the 1,066 that a family of size 4 with $4,000 of debt living in the northwest sector, that is sector 2, would pay, versus that same family living in the southwest sector, that is location 1, and that's $109.34, which is the estimated regression coefficient associated with location 2. The estimated regression coefficient associated with location 3, given a model in which location 1 is the benchmark, is minus 80.64. What's it mean? Well, what it means is a family of size 4 with $4,000 in debt living in the northeast section pays on average $80.64 less than that same family profile living in location 1, which is the southwest sector. Well, we know that to be true because when we take a look at someone living in the northeast sector versus someone living in the northeast, I'm confusing you here a little bit. I don't mean to. But when we take a look at the difference between someone living in the northeast versus the southwest, section 1, that's 876 minus 956. That's where we get our minus $80.65. So again, what do these estimated regression coefficients associated with Loc 2, Loc 3, and Loc 4 represent? They represent the difference associated with living in those locations versus the same family profile living in location 1. So I'm going to ask you, and I apologize for getting a little bit miscombobulated there in the arithmetic, but when you take your time and go through it and actually analyze the numbers that you see on these worksheets, I'm hoping that it's clear what these estimated regression coefficients associated with our indicator variables represent. Now, we can do all kinds of complicated model building using qualitative variables in conjunction with quantitative variables, and we will do some of that most certainly in the Math 431 follow-on linear regression 2 course. And there's other things in the reading for this particular week's lesson that you should concentrate on about model building, etc. in chapter 9, but I did want to take the time to explore with you in some detail how these indicator variables work and how to interpret the estimated regression coefficients associated with them. Now, I suppose as a final little thing you might want to do is you might want to take a look at a model using, say, Loc 3 or Loc 2 as the indicator variable left out of the model. And you're going to see that you're going to get these same y hats, of course. You're going to get the same y hats. But then the difference between the locations that are in the model versus the location are not in the model are going to change the values of your estimated regression coefficients. But the relative difference is not going to change at all, because those differences are based on the y hat values, which don't change given the estimated regression model that we happen to have built. Okay, the conclusion, well, it's the same as my conclusion today is the same as it's been for every lesson that I've produced, and that is read through the examples in the textbook, make sure that you navigate through the suggested homework problems and their solutions, which I provided for you via links in our weekly lesson. Pay attention to the reading. Certainly look over those items in the reading assignment that are not addressed in this particular video presentation, and continue to build your base so that you can finish this particular course strong and begin the follow-on course with a real good foundation as to how to build and interpret some of the basic multiple linear regression models that we'll encounter. And then we'll get, in follow-on presentations, we'll get a little more sophisticated in things that we'll explore.